Welcome to section 12.4. We're dealing with limits, but this time, instead of taking a limit towards a specific value, we're going to go back to the end behavior idea, and we're looking at limits in terms of infinity. And so what we want to do is start with this function 4x plus 3 and x plus 1, and we want to look at the graph. And so what I want you to do is put this in your y equals. Don't forget to put in value, parentheses around the top and the bottom. And so I want to look there. And so what I'm going to do is go to my graph as well. 4x plus 3 divided by x plus 1. Okay, and we want to look at the graph. Oh, let me go to the graph instead of the table. Now take a look. We want to talk about kind of what happens, and I want to go back to some of the rational function idea. So I'm going to move this down to try to get it out of our way, but I do want to talk about this rational function, and I want to look at the fact that I know there's an asymptote, so I want to go back to its function. If I have f of x equals 4x plus 3, let's try that again, 4x plus 3 and an x plus 1. We know the vertical asymptote is at -1, x equals -1 based on the denominator. And so I can put in that vertical asymptote, and you can plug this on your graph. I just kind of want to show it to you. We know the horizontal asymptote comes from dividing the coefficients because there's an x value on top and bottom. So my horizontal asymptote is at y equals 4. And so if I go up 1, 2, 3, 4, my line is not very straight, but I have this horizontal asymptote here as well. Now what we want to do is we want to look at what happens in part A as f of x gets bigger and bigger and bigger. You have a problem though with your graph. Your graphing window is from -10 to 10, and the problem is we want to put in 100,000. You cannot do that unless you change your window. And so what we want to do, let me go here a second. I want to go to window. And I want to start at, I'm just going to start at 0, because really they just want from 10, 100, 100,000, so on and so forth. But I'm going to go all the way up to 100,000. Oh, too many. So I'm going to go up to 100,000, and I'm going to go up then by like 10,000s. Something huge kind of as we're looking, and all I want to change is my x's because that's what I'm looking to plug in my graph. Now if I go back to graph, you'll notice now that it kind of looks as if I just have a straight line. The problem is you can't see, let me get rid of all of this, you can't see the fact that it actually did curve. It curved past here at -1, right? It curved and went down. But because we're going here by 10,000s, you're not going to see that. The problem is I need this in order to be able to complete my table, because if I want to try and pick a value, let's say I hit my trace button, I can pick any value I want. Let me start with 10. If I pick that x is 10, we can see then that y is 3.91-ish. If I want to do 100, we see that you get 3.99. Okay, if I want 1,000, oh, one more error again. If I want 1,000, we get 3.999. And so our goal is to look at all of these enormous values. The problem is I can't do that without actually changing my window. And so here's what happens. Let me go back to our notes. And we want to put this in. So if I put this in, we noticed at 10, you get 3.909, 3.990, 3.999, 3.9999, 3.99999. Okay, so as we look at this, we are asking you basically, as x gets bigger and bigger and bigger and bigger, where do we get closer to? We can kind of see that we get closer to 4. Now the way that works notation-wise, we say the limit as x approaches positive infinity of my function, and I'm just going to shorthand this f of x, we can see this is going to 4. Okay, so what happens is it becomes smaller and smaller. Now you'll want to go back and change your window again to negative 100,000, but we're now taking the limit this time as it goes to negative infinity of our function. Okay, let's look at what happens. At negative 10, I get 4.111, 4.01, 4.001, 0001, 00001. Well, where does it look like it's going? I think we could say the same thing. It looks like it's going to 4, and so we have now a limit as we go to negative infinity. We are really talking about end behavior, and that's kind of this idea. We're going back to this idea of end behavior, and where is it now approaching? The thing is, in this section, it's going to be approaching a single number, where some of the stuff we did in Algebra 2 approached infinity or negative infinity, things like that. Now, in the previous 2 examples, we looked at finding the limits at infinity. And we looked at it in 2 ways. We can take the limit as x approaches a positive infinity of a function. We got one number. We're going to call that L sub 1. The problem is we also looked, let's try again. We also looked at the limit as x approaches negative infinity of our graph. In this case, we got the same value, but I'm going to call it L2 because sometimes that's not going to be the case, where sometimes you might get 2 different values. But I want to keep this idea, okay? And so what we have done for this intro is really looked at the idea of an end behavior graph and as it approaches a specific number. So what we're going to do is look at different limits of infinity and then use them to help us actually evaluate limits. So let me slide this down. All right, here we go. Actually, let me go a little bit farther because I've already done that. There we go. All right, take a look. What we want to talk about is the fact that as x gets really, really big, what's going to happen? Well, if I look at 1 over x squared, let's pick some really, really huge number. Like let's suppose, x is, I don't know, 100,000. I don't know, you can do that. If you put in your calculator 1 divided by 100,000 squared, you get 0.0000 e to the whatever. You get something really, really close to 0. So as you're looking at this idea of these fractions, when you put a bigger number and you divide 1 by this really huge number, you're going to get closer and closer and closer to 0. So I'm going to do the same thing. As I look at this, I'm going to take 5 minus this. Well, if I put a huge number, again, if you assume this is 100,000, you're getting something really huge. This fraction right here goes to 0. So what I really have is 5 minus 0, which is just 5. And so the limit of this is 5. And so any fraction, basically, as we're looking, when you take a fraction and you divide it by an x, as x gets bigger, your fraction is going to go to 0. Okay, well, take a look at number 1, though. Like, I don't have any fractions, so how do I make this work? What we're going to do is divide numerator and denominator by the highest powered term. Okay, only, though, in the denominator. You're going to use the denominator to help. So here's what we do. We have this x squared. And so the way it works is we're going to divide by x squared. Okay, so as we go through, we've got negative 2x over x squared plus 5 over x squared, 4x squared over x squared minus 1 over x squared. Now I'm going to simplify this, and what I'm going to do is take the limit as x approaches infinity. Positive or negative, it won't matter in which direction. Okay, so take a look. If I simplify this, 1x cancels with 1x. I have negative 2 over x. plus 5 over x squared. X squared and x squared cancel, so 4 minus 1 over x squared. Now, as this approaches infinity, any fraction with an x in the denominator will turn to 0. So I get 0 plus 0 all over 4 minus 0. Well, 0 over 4 is just 0. I'm going to put that down here so I don't run out of space. So this ends up giving us a limit that approaches 0. And so the key basic idea is that when you take the limit to infinity, any fraction with x in the denominator will go to 0 because you're going to make it bigger and bigger and bigger, so the fraction is going to get smaller and smaller and smaller. So let's try again. We're going to divide by x squared. So I have 3x squared over x squared minus 4 over x squared, 2x squared over x squared plus 7 over x squared. All right, if I start canceling out, I get a 3 minus 4 over x squared. These cancel, so 2 plus 7 over x squared. Now, as I take the limit as x approaches positive or negative infinity of the fraction 3 minus 4 over x squared, 2 plus 2 over x squared, 7. Let's try and make this correct. This goes to 0, this goes to 0. So what fraction do I have left? 3 over 2. Okay, and again, this is an idea for rational functions, when you're dividing a polynomial by a polynomial. Let's try one more just to make sure. We're going to divide by the x squared. So 4x cubed all over x squared plus 2x over x squared all over an x squared divided by x squared minus 4 over x squared. All right, let's do some canceling. 2 cancels with 2, so I have a 4x. This one cancels with 1 here, so I have a 2 over x. This gets me 1 minus 4 over x squared. Well, as I take the limit as x approaches positive or negative infinity, I'm just copying this down. Okay, what happens? This goes to 0. This goes to 0. What happens though when I put a huge number in? This is our problem area. Let me change colors because it's our problem area. This, what happens when I take 4 times a really huge number? I get a really huge number. Because it goes to infinity, we said that was one of our problem areas a couple of sections before. Our limit does not exist. And so kind of keep that in mind as you're going through, that you really have to be careful that if you know you're left with an x, when you try to put in a number bigger than that, or huge, you still get a huge number. So, okay, there are some rules. You can remember the rules, or you can just go through the process that we went through as well. Here's what happens. If the degree is less in the numerator than it is in the denominator, like number 1, we get that the limit is 0. If, like in number 2, the degree of the numerator is equal, so I had a 3x squared and a 2x squared, then we divide their leading coefficients. So I'm going to use the ratio. Ratio of leading coefficients. And the last one, if the degree in the numerator is bigger than the degree in the denominator, then our limit does not exist because you have something then that's an unbounded and therefore cannot find the limit to a specific value. Okay, so this kind of gives us some ideas. What we're going to do is take a look at an application of why we use this dividing up. So let's flip to the back. Okay, let's go back to sequences. Now this is what we're going to study in chapter 9. Those of you that aren't seniors, we're going to go back and look at some of this stuff. But here's what happens. If I want the first term in a sequence, then I plug number 1 in for n. So 3 times 1 is 3 plus 2 is 5. And 1 plus 1 is 2, 5 halves. I'm going to write it as a decimal, and I normally don't like it, but it's going to help us kind of figure out which value it goes to. If I do that for 2, I get 8 over 3, which is 2.67. If I do that for number 3, number 3 gets us 11 over 4, which is 2.75. If I plug it in for 4, I get 14 over 5, which is 2.8. And for 5, I get 17 over 6, which is 2.83. Okay, now that's great, but I'm looking at this and I'm seeing that it looks like it's getting closer to 8 something, 2.9. The problem is these terms are all so close together that I just don't know. So I'm going to pick something huge and see if that kind of helps me. So I'm going to try to find the 1,000th term. If I plug in 1,000, I get 3,002 over 1,001. Now this approximates to 2.999. Now, looking at a value like this, can we tell where I'm approaching? Absolutely. In this case, it looks like it goes to 3. So what we say is the limit as n gets closer to infinity. So as I get really, really big values for n, of my sequence 3n plus 2 over n plus 1, I get closer and closer and closer to 3. Now, because the sequence gets closer to a value, and this is because of sequences, we say that the sequence gets closer to some value than the sequence is said to converge. If the sequence does not get closer and closer to a value, then we call it a diverging sequence. And so this is one kind of look at it. And again, we're going to try and get you to look at this idea of converging and diverging because we're going to talk about it in chapter 9 anyway. So let's take a look. We're going to do one last example that mixes everything together. My favorite. Okay, take a look at the following sequence. Does this sequence converge or diverge? Okay, well, I want to start kind of first by looking at, can I find the first couple of terms to see what happens? Well, okay, sure. So here's what I'm going to do. I'm going to do a little work here. The first term means you plug in a 1 for n. So 8 over 1, because 1 cubed is 1, okay, times 1. 1 plus 1 makes 2. 2 times 1 plus 1 is 3 all over 6, which really gives me 48 over 6, or just 8. So the first term is 8. All right, let's do the second term, and then I think you can kind of get at the idea. 8 over 2 cubed. 2 cubed is 8. So I have 2, and 2 plus 1 is 3, and 2 times 2 is 4, plus 1 is 5, all over 6. Okay, well, I'm going to cancel these out, and 2 times 3 is 6. I'm going to cancel this out. You get 5. All right, if I went farther, you would get this, 4.15. And so we can kind of see that it's getting lower and lower. The question is, does it go to a specific value? If it goes to a specific value, we say converge. If it doesn't, we say diverge. Okay, so here's what I'm going to do. I'm going to try and find, as n goes to infinity, if the sequence actually does converge or diverge. So as I'm looking at this, 8 over n cubed, n plus 1 to n plus 1 all over 6. What I'm going to do is try and simplify this a little bit. So I'm going to do a little work ahead of time. So 8 over n cubed, let me see if I can simplify this. I've got this n outside. If I FOIL these two, I end up getting 2n squared plus 3n plus 1. And if I multiply 8n into that, what I end up getting is 16n cubed plus 24n squared plus 8n, all divided by 6n cubed if I multiply these. All right, so let's go back to what we did before then. The limit as n approaches infinity of this idea, because I have an n cubed, I'm going to divide by n cubed. So I have 16n cubed divided by n cubed plus 24n squared divided by n cubed plus 8n divided by n cubed all over 6n cubed divided by n cubed. All right, here we go. Let's do some crossing out. So I take the limit as n approaches infinity from either direction, if you'd like to write it. 16 plus, 2 of them cancels with that, so I've got a 24 over n. 1 cancels with 1, so that's a 2, so 8 over n squared, all over 6. Well, as I go to infinity, these two values get closer and closer to 0, so I have 16 over 6, which reduces to 8/3. Because I'm able to get a specific number, we say this series converges. And what that means is as I get to bigger and bigger and bigger values of n, my series, or my sequence is going to go directly to a value of 8/3. So that's the idea. So we're mixing in a little bit of chapter 9 in with chapter 12, so that by the time we go back, you've actually kind of have an idea of what's going on. So that's it for section 12.4. Thanks for watching. Again, try whatever homework you can before we get to class, because this is a little bit different.